Hi, I'm Sala, and in this video we'll finish an example of linearization of a function of two variables by discussing the numerical accuracy of the obtained approximation and plotting the approximation error relating it to the Hessian. If we recall, in the first video we defined the function to linearize. We chose an operating point, the point of tangency. The value of the function at that point was 0.92, and with this multivariate Taylor series expression of a smooth function, we said that if we took just this stuff, we had the linearized model, and furthermore, if we wrote just this fragment, then we had the linearized model in incremental coordinates. And as linearized models were widely used, this thing was expressed in matrix form by this 1 times 2 Jacobian matrix times this vector, 2 times 1 column. Jacobian was a row. And even if they were not used in the linearized approximations, this quadratic expression was able to be written with this Hessian 2 times 2 matrix of second derivatives and left and right multiplication by the increments. Of course, all this here will be the linearization error, the difference between the actual function and the linearized approximation. And of course, if delta x is small, the linearization error will be somehow quadratic. The Hessian will play a key role. In a particular example, the Jacobian at the operating point evaluated to a number gave me this thing, which were the slopes of a linearized model, the slopes of the tangent plane, that, written like this, but explicitly solving for y, I got this equation, so I did plot the function and the tangent plane. So let's do a numerical check of the accuracy of the linearization in just one point. We'll compute the linearization error, and then we'll also plot the linearization error in a range of points to get the feeling of what we are doing. Then, for instance, I will have a small increment around the operating point of minus 0.04 in x1 and plus 0.03 in x2. So the linearized model is just multiplying the numeric Jacobian 1 times 2 times the column vector of increments, and then that will give me 0.0582 as the approximation of the increment of the function. If instead of incremental units I want to compute, well, the actual point on the plane in absolute units, then it's 0.9787. So let's check what was the exact value of the function to get the error. Well, this will be my new x in absolute units. The actual function swallows absolute x1, x2, not increments. Incremental stuff is useless for the original function. So we get the new x, this point, and then this is the correct evaluation of my function numerically at this new point, and it is 0.98. So, 0.9787, it's, well, a sensibly good guess. Indeed, we have this 0.0013 linearization error because, well, the correct increment of the function was 0.0595 and my approximated linearized increment was 0.0582. Well, this is the numerical analysis of the error at a given single point, but we may compute the linearization error as, the true f minus my linearized approximation in this tangent plane. And instead of doing a surface plot, I will plot now a contour plot with f contour at a given list of levels for a pretty figure. And then here we have the linearization error. Of course, linearization error is 0 at the operating point, because if increments of x are 0, then increments of y predicted are 0. We are at the operating point. But then we have these contours that somehow resemble ellipses close to the tangency point. And, somehow they deform due to the nonlinearities. Later on, ellipses are quadratic forms, and the deformation of the ellipses are due to the cubic, quartic, or whatever extra terms of the Taylor series, because in fact, if we analyzed what happens close to the operating point, then quadratic terms will be dominant, and this will be the most important term in the linearization error, i.e. the Hessian plays a key role. Indeed, this linearization error quadratic will be a parabola if the Hessian has two positive eigenvalues, because, x1 squared plus x2 squared or something like that is a paraboloid in 3D, let's say. And this is the case. These are two positive eigenvalues, so the Hessian is a positive definite matrix. Then the linearization error, this thing will be positive, the function will be above its linearization. And indeed, this is what we see when looking at this figure. So locally, the error is kind of a parabola above the plane, because the Hessian has two positive eigenvalues. If it had two negative eigenvalues, the error would be a paraboloid, let's say, but below the linearization. And if it had positive and negative eigenvalues, then the error shape will be sort of a saddle, and the contour plot will not have an elliptical form, but the form of hyperbolas. In this case, we have this kind of ellipses that get distorted by cubic and higher order terms as we get far from the point of tangency. So this is kind of the analysis of the linearization error, but in introductory courses, maybe the only analysis you need is the one we did at the beginning, just numerically in a point, comparing this increment to the true increment, evaluating the nonlinear function at the new point. So, with this numerical and graphical analysis of the linearization error, we finish the video here. Thanks for watching.